we have been talking about recap of classical theory of computation, that is computability theory of discrete data, computability theory of finite sequences of bits, and finite sequences of natural numbers, decision problems. So let me briefly recall where we ended last time and then proceed from there. Our goal for today is to finish that recap on discrete computability theory and to start with discussing real computability theory, in particular notions of computability for real numbers and for real sequences, and later also for real functions. And it is crucial to find the right notions. It's easy to take a wrong and unsuitable definition, and with unsuitable definitions, of course, all results are both meaningless and usually also lack elegance. So, but first, let's recall discrete computability theory. Right, namely, we have formalized what it means to decide a subset of natural numbers. That means to compute its characteristic function. Particularly, deciding means always give an answer, the correct answer, whereas semi-deciding means to only give positive answers, and instead of a negative answer, give no answer at all. And that has turned out to be a justified name because the problem is decidable if and only if the problem and its complement are both semi-decidable. So that's kind of really half of deciding a problem. And we've also discussed, formalized what it means to enumerate a set. Namely, where deciding and semi-deciding amount to kind of input and then give an answer about properties of that input. Enumerating is all about output, namely list in a certain order, not necessarily increasing order, all elements from the set L. Don't exclude any, don't repeat any, it's supposed to be injective, and don't list elements beyond the set L. And we've seen examples and properties, and then we have proceeded to compare decision problems by notions of reduction. And the problems which we have compared using reduction are the three problems: the holding problem, the non-triviality problem, and the totality problem. And first we've seen that all of them are indeed undecidable, but there are differences, there are degrees of undecidability, and such degrees, such differences in undecidability can be investigated using this partial order on decision problems, namely a way to compare two decision problems if there's a computable translation from one to the other that maps positive instances, that is yes instances of the first, to positive instances, yes instances of the second, and vice versa, negative instances are mapped to negative instances. And this notion of reduction has turned out, we have confirmed that this is justified. It conveys the intuition that the first, the set on the left, is at most as hard as the set on the right. So that's the intuition behind this partial order. And furthermore, for partial order, of course, we want it to be transitive. So it's transitive, it's obviously reflexive, but it's not necessarily antisymmetric. And using this notion of reduction, we have been able to compare the above problems and in particular to establish which of them can be reduced to which ones and which, interestingly, cannot. And in particular, The totality problem is undecidable like the other ones, but it is in a sense more undecidable. Namely, one can reduce any of the other two problems, the halting problem and the non-triviality problem, to the totality problem, but not the other way around. Provably, this is impossible, which means that the totality problem is strictly more difficult, whereas the halting problem and the non-triviality problem can be reduced one to the other, and then therefore they can be considered as equally undecidable. Okay, and the reason why we recall this is a careful selection from a broad field of classical computability theory, is because we will be interested and learn about corresponding notions, for instance, of reduction or continuous problems, where the classical notion doesn't apply, and therefore one could not, so far, for instance, define numerical problems to be uncomputable, or one could not define numerical problems to be something like NP complete, which of course is possible and common for discrete problems as a refinement from computable reduction here to polynomial time computable reduction. So generally, the topic of this lecture is take classical discrete notions and extend them, generalize them in a careful, suitable way to real problems, to continuous problems, and thus extend computer science from the discrete to the continuous realm to be able to make rigorous statements about numerical problems and their computability, uncomputability, and complexity. And in this lecture, we avoid the Turing machine and instead consider polynomial time equivalent, but arguably more practically relevant model of computation, namely while programs, which were defined as these operations. So while program has finitely many variables. It has addition, subtraction, well, only of natural numbers. So when the result is negative, it gets truncated to 0. It has division by 2 with truncating. So if an odd number is divided by 2, it gets rounded down. And it has this eponymous while loop construct that gives rise to its name. That means executing a loop body P as long as the loop variable xj is non-zero. So the loop body better modify that. And we needed ways to encode while programs, and which particular way is usually not so important. One way is, for instance, to encode it as an ASCII sequence of bytes first, and then the sequence of bytes as one very, very large integer. And the UTM theory about computability says there exists something called a universal Turing machine, but of course, in this lecture where we don't talk about Turing machine, it's basically a universal while program, namely a while program that can receive, that takes as argument, as input, another while program and an input for that while program, encoded using Hilbert's pairing function, possibly as one single natural number argument. So if we have several or even a varying number of arguments, we can always combine them into one single natural number by using this pairing function. And this is something that's only possible in the discrete realm. It will turn out that it is impossible to similarly combine several real numbers into one single without, well, one can of course combine them, but then it's not possible to computably or even continuously recover the individual parts of the real combined real number. Right, and that's basically where we stopped last time. So to continue the discussion, I want to talk a little bit about currying, that is basically type conversion, right? So currying is named after Curry-Haskell, right? So there are two famous things named after him. First, the currying operation is his first name, and then the Haskell programming language after his second name. And currying, well, technically, historically, currying was invented before him, at least by someone called Schönfinkel, but somehow the term currying has been established. And in order to formally describe this and other operations on programs, right? So in a sense, we're now talking about operations on programs, whereas the previous part of the slide was concerned with programs operating on natural numbers. But by talking about operating on programs, well, that basically also amounts to operating on natural numbers, because every program, as you recall, can and is considered encoded as some possibly very large natural numbers. So when we talk about operating on programs, that basically is just again the same as operating on natural numbers. It was important, for instance, to prove undecidability of the holding problem. On the other hand, operating on programs allows us also to operate on functions, namely the functions computed by a program. Every program computes a possibly partial function from natural numbers to natural numbers, right? So that means when we operate on natural numbers, we also can use that to operate on functions, on those functions that can be realized using a while program and taking the while program's code as a natural number. So, right, I want to talk about currying. And currying, to illustrate this concept, recall, for instance, from classical calculus, the function of two variables. So here you see a function of a real variable x and of another real variable y. And there are different ways of how to look at such a function of two variables. One way is by fixing the one argument and considering it only as a function of the other argument. For instance, we could fix y to be equal to 0, then e to the y is equal 1, and then this basically boils down to just the ordinary sine function, sine of x of one variable x. Alternatively, we could also fix a different value of y, for instance, y equals 1. Then this is again an ordinary function of one variable x, but now a scale one, right? Then we scaled by e 2.7. Or we could fix y to be equal to -1, in which case this is again the sine function, but scaled down. So that's one way of looking at this function of two variables, by fixing several possible values for the second argument and considering it as several functions of one argument x. Or, of course, we could do it the other way around. We could fix the first argument. For instance, we could fix x equals 0, in which case it's a function of y only, namely the 0 function. Or we could fix x to be equal to pi, and again it's the 0 function, and so on. So the baseline on currying is that functions of two or more variables can be considered equivalently as a family of functions where one argument is first taken and then fixed, and then the remaining is a function of one argument, or vice versa. One could consider a family of functions of one argument and kind of combine them, string to glue them together to arrive at a function of two arguments. So, and can we do the same computationally? The answer turns out to be positive, and this is exactly the SMN theorem. The name from the theorem comes from the initials of the authors in computability theory that established and proved the theorem. The proof is not too hard, but the importance, the relevance of this theorem in many applications in computability, that's what makes and made it famous. So the theorem says Basically, there exists a while program that executes, that performs such conversion of a function with two arguments, given one argument into a function of the other argument only. And how does that work technically? Well, we're given a program, an encoded program of the function with two arguments. And this is what you see here. So remember, this symbol means the code of, and this means the program. And the code of this program is a natural number. And this is supposed to be a program of two arguments, or this program is supposed to compute a function of two arguments, and the and there's an input of one argument, namely the x. And the goal is to convert this program with two arguments into a program that only accepts the y as argument, only one argument, and fixes x to this given value, basically by hard coding the argument x as a constant into this program. And this is the intuition, this is the proof sketch, and the formal approach is, or the formal statement is, you can see here. It returns a code of this program where the first argument has been fixed to x, and only the second argument is still considered as free as to be given. So that this, again, is a program of only one argument, and the code of that program, this is what's output by the given while program. The given while program receives a program code and outputs another program code, where the output program is defined in the way I just said. Maybe it converts the two variable argument into a one variable argument where the first variable is fixed. Another theorem about operating on programs and their codes is the universal Turing machine theorem, that the while program can simulate any other given while program given by its code. There exists while program that, given the code of another while program, executes this while program. Or put differently, here's another version, namely a counterpart actually to the SMN theorem, where we're given a program. So this P is supposed to be a program that outputs the code of a univariate function. Let me say it again. Suppose that P receives an argument x and outputs the code of a function of one argument y. This is what you see here. So P of x outputs a natural number, and these inverse brackets mean interpret this natural number as the code of a program, namely the code of a program which receives another natural number argument y. And the statement says, given such a code of a program, it is possible there exists a y program that converts this program into one that actually computes the two-variate function, namely first use the first argument to recover the code of a program, then turn that code of a program, then execute that code of a program in this with the second argument here, and return the value of that. And this conversion is computably possible according to the UDM theorem. And the third statement is that while program can kind of can realize the composition of two while programs. We know that when we have two while programs that compute functions, then it is possible to compute their composition. The computable functions are closed under composition. But the statement here is a little bit subtly stronger. Namely, it says it is possible to convert two programs into the program that computes the composition of the two programs. Namely, that return the code of a program which computes the composition. So these are three statements about operations on programs, on while programs, and thus operating on the functions computed by this while program. So that's why it's called operators, namely it operates on functions. Right, and the last part, 3 slides of this recap on computability theory in the discrete realm is about Oracle computation. And we recall that, well, first because Alan Turing's PhD thesis on the Alonzo Church was based and evolved around that. But secondly, because Oracle computation will be highly relevant when we talk about real computability and more generally about real complexity theory. So that's why we better recall this notion. So what is an Oracle Turing machine? Well, fortunately, you don't need to know because remember, we avoid Turing machines here altogether. Instead, we talk about Oracle while programs. So this is for your convenience, a reminder of the classical while program with its operation. And now we throw in a new operation, namely kind of imagine a subroutine call, calling some external function phi with an argument xi. So this is a function of one argument, although as you remember, we can also have several arguments combined into one, so this is no loss of generality. And the function, well, it returns some other value, which is then stored into another variable xj here. And what kind of function phi is this? It's some arbitrary but fixed total function. So put differently, Oracle while program can make a function call to one specific fixed separate function. If this function is a computable function, then of course we can replace that with a code, with a while program that computes, that realizes this function. But more interesting actually is the case where phi is an uncomputable function which cannot be replaced by a while program, and therefore making a call to it strictly enhances and increases the computational power of that while program. And well, this is not necessarily practically realistic, right? Making a function call to an uncomputable function, that's actually technically impossible. But this gives rise to another way of comparing decision problems, and more precisely to study computability on higher levels beyond the, for instance, the halting problem. And one such example is the case where this external function is the characteristic function of the halting problem, namely where we're making a call to this function with xi. Xi is interpreted as an instance of the halting problem, namely as an encoded pair of an algorithm and an argument to that algorithm. And the question is, which is answered by this function call, whether the given program terminates on that given input. This is a halting problem, and in this way, allowing a while program to Oracle access to the halting problem allows it to decide the halting problem or even more complicated problems. So when we put the superscript phi to the program to indicate that phi is the function that the program can call, we can actually replace that function, we can replace that Oracle, and the program will still make the same calls to this external. Yeah, this is like in linking, right? So we can link some library to our program, so that when the program performs some library function, it will be executed in the library and performed by the library. Or we can link our program to another library, and the program will not know it, will just have the effect that the program makes when it makes a function call to the library function. This call gets transparently directed to another function by a different library. And the library functions, kind of the external function we're interested in, include, for instance, the characteristic function of the halting problem as indicated here, in which case we just put a superscript h next to the program rather than some function symbol like phi, and we understand that the decision problem is always understood as a characteristic function and thus as a function problem. Also, for now and here, we only consider total oracles that always return an answer, natural number or 0, 1, for instance. Later, much later, we will have to also deal with partial oracles. Okay, and what I want to discuss or exemplify here is one possible application is sometimes so-called Schoenfield limit lemma. So there's a, yeah, it's named after Schoenfield, a computability theorist, but again, interestingly, it was not really him who invented this lemma, but still, it nowadays is known under the name Schoenfield limit lemma. And to illustrate and demonstrate or explain its statement, let's consider a function, call it g, a partial function from natural numbers to natural numbers. So only one type of argument. And let's suppose that this function is h computable, where h means computable by a while program with oracle access to the characteristic function of the halting problem h. So this is in general not a computable function, right? Because the while program can make oracle calls to this halting problem, which cannot be replaced by an ordinary while program without oracle. But Schoenfield's lemma characterizes what kind of functions can be computed in this stronger, in this enhanced sense with access to the halting problem. Namely, these are precisely the pointwise limits of ordinarily computable functions, functions that are computable without any access, oracle access to the halting problem or anything at all. So pointwise limit, that's a statement. Pointwise limit are basically the same as having oracle access to the halting problem. So the interpretation, this interpretation of the limit lemma is actually very important. So let me repeat it. The ability to compute pointwise limits, that's a very powerful operation of pointwise limit. Namely, it is in general as powerful as having oracle access to the halting problem, which we know is very powerful because the halting problem is undecidable. Okay, and I keep emphasizing this because we will see in the real realm that a similar statement holds, and thus gives rise to this very strong distinction between approximating real quantities with error bounds or without error bounds. So this corresponds kind of to the case without error bounds, which corresponds to oracle access to the halting problem. So, right, let us briefly recall what does it mean to have pointwise limit. In this case here for now on integers, right? Later we will talk about limits of real numbers, which is all you know about from in calculus. But here, this is a limit of sequence of natural numbers parameterized by the argument x, and the sequence index is j. And when does the sequence of natural numbers converge at all? And where does it converge to? There's only one way for a sequence of natural numbers to converge, namely when it becomes eventually constant, eventually stable. So initially the natural number sequence may kind of like fluctuate, but eventually it must be stagnant in the sense that for all sufficiently large indices j, the value must be the same, it must become constant, right? That's because on the natural numbers we have the discrete metric, the discrete topology, so that any convergence means eventually being constant. So let's now sketch the proof of this limit lemma with its both direction, it's an if and only if, it's an equivalence. And for the first direction, let us suppose that G is the pointwise limit of a computable function, computable without Oracle access. How can we kind of get rid of this limit and replace it with something that does not eventually converge, but just outputs the value g of x and then stops, right? That's what it means to compute an integer function, output the value, stop, and that's it. No limit, no infinite sequences. But now this computing g is granted, is given Oracle access to the halting problem, whereas the original function is not. And in order to perform this conversion from the pointwise limit computable function f without Oracle to the finite time computable function g with Oracle access, right. Yeah, before proving that, let us also extend the notions of decidability, of semi-decidability that we discussed previously, and of the halting problem to the case of Oracle while programs. Namely, also here in this case, we always put a superscript, namely the Oracle function, onto the program. So P with superscript phi is a while program with Oracle access to this external function phi, and we say that it decides a set if it computes its characteristic function. We say that it semi-decides a set if it terminates. Well, basically it's all the same definition, but now extending from ordinary while programs to while programs which have been given Oracle access to this external function. And also then we arrive at a Oracle version of the halting problem. Maybe the Oracle version of the halting problem is the question, given the code of a program, the code, just the code, and an input to that program, when executing this program code with Oracle access to this phi, does it terminate or not? This is the Oracle version of the halting problem. And if we consider different oracles phi, then this become different halting problems. And we recover our original while program, our original decidability, our original semi-decidability, our original halting problem when the function, external function, is in a sense trivial. Maybe it's just a zero function, for instance. That's then every call to that zero function can, of course, and obviously be replaced by an arbitrary just returning the value 0 without any function call, and therefore as an ordinary while program without Oracle access. So the interesting cases are when phi are undecidable problems, such as, for instance, the halting problem. And then we get here a higher order halting problem. And let's suppose phi denotes the characteristic function of the halting problem. Then termination on input x is even harder to decide, right? Then you can adopt our initial proof of the undecidability of the halting problem to show that this higher order halting problem cannot be decided by any Oracle program that has access to this Oracle phi. So that's kind of the generalization of this initial proof. And we indicate this higher order halting problem with H prime. So that's a halting problem for while programs which are granted Oracle access to the halting problem. And this gives rise to a hierarchy. We can iterate that. We can consider while programs that have Oracle access to H prime and consider the halting problem for such while programs, which gives rise to H double prime and so on. And we'll discuss that hierarchy in a few minutes at the last slide of this recap chapter. But first, let's proceed to prove Schoenfeld's limit lemma, because, well, not because it's so interesting but because it both the statement and its proof will later be generalized to continuous functions, to real functions from the current setting of integer valued function. Okay, so what is the proof? So I already mentioned one direction, namely what does it mean for y to be the limit of this sequence, right? And it means that the sequence eventually becomes constant with value y, and that means there exists a capital J, so that for all sufficiently large indices small j, sufficiently large meaning having value at least capital J, the function value is constant, is stagnates, is equal to this initial y. Okay, and this equivalence is kind of obvious, right? And this equivalence gives rise to our one definite direction in the proof of Schoenfeld's limit lemma, namely, if G is the pointwise limit, then we can compute it using oracle access to the halting problem as follows. Observe, let's fix some value capital J. Then this is a universal quantifier over infinitely many arguments. So can we decide whether this is true? Well, naively, we cannot decide because it requires testing, trying infinitely many values of small j. Requires trying with j plus 1, capital J plus 1, capital J plus 2, capital J plus 3, all yield and output the same value y. And this is not possible in finite time to decide because there are infinitely many values to test. But now we have this access to the halting oracle, which allows us to kind of turn that test, trying infinitely many values of j, have a Turing machine do that, have a while program do that, and then ask whether this while program terminates as the halting oracle. So more precisely, let's consider while program which tries for fixed j, tries all possible values small j, and if each value small j satisfies this condition, so given capital J and given y, try all possible values of small j. If all of them satisfy this condition, well, then try the next possible value of small j. There are infinitely many candidates, right? Only once some value of small j turns out to violate this condition, then terminate. This is going to be our new while program. And observe that we've constructed this while program in such a way that it terminates if and only if this condition, including the universal quantifier, is wrong. Okay, we say it again. If this here is true, then the while program we've just constructed will keep running forever. We'll try the next value of small j, the next value of small j, always keep on trying indefinitely. Whereas if this condition here is false, if the universal quantified formula is wrong, then the while program we've just constructed will terminate. So that means by asking our oracle, halting oracle, whether this while program we've just constructed, whether it terminates or not, that allows for our new while program to test whether capital J satisfy this condition or not. Okay, so we've kind of traded this universal unbounded quantifier, which is undecidable, to a decidable property by using the oracle access to the halting problem. And now our new while program can simply test all possible values of capital J until it has found one. And it will search, keep searching, and will succeed in finding one if and only if this limit exists and is equal to y. And in this way, we can convert a program that computes this limit. Well, for some arguments x, the limit may not even exist. It may never stagnate. For others, it may exist and produce some value. And using this argument, we can convert that program with limits into another while program without limits, but in turn, give an oracle access to the halting problem. And thus proves one direction of the Schoenfeld limit lemma. But the limit lemma is an equivalence. It also makes a claim about the opposite direction. And in order to establish the opposite direction, here's some proof sketch And that's actually pretty subtle. So if you don't immediately understand it, I'd like to encourage you to review the video. There's a reason, that's one of the reasons why we put the recorded lecture videos online. And also, Schoenfield's limit lemma is a classical topic in computability theory, which you can easily look up and study by yourself, for instance, on Wikipedia or any textbook. So that's standard material, and the purpose we created here, as I mentioned, for recap purposes in the course, we're going to generalize that setting from natural numbers to real numbers. Okay, so the other direction which we're now trying to prove is the following. Let's suppose we have a while program with Oracle access to the halting problem that computes the function without limit. So it will just eventually output the value y and then stop, right? And now we need to be able to simulate that program without having access to the halting problem. But on the other hand, we don't need to produce the answer right away, but only output a sequence that eventually converges, that eventually becomes stable and equal to the limit. And to this end, we're going to use the following very interesting technique. Namely, we're going to consider two disjoint and finite subsets of natural numbers. I like to call them A and B. Initially, they're both the empty set, but as our simulation proceeds, our simulation will need to work without Oracle access to the halting problem. It will need to replace all queries, all calls to the halting Oracle with something else. But on the other hand, it doesn't need to produce the result right away, but only in the limit. And the two sets A and B that we're going to consider are the sets of queries that the program computing the G with halting Oracle makes, because this is kind of the queries, that's what causes us problems. We need to avoid and remove those queries and answer them without Oracle access. And instead, we're going to look whether this queries belongs to the set A, finite set A, or to the finite set B, which are initially empty. And A, imagining this to be the set of, to be a finite subset of the halting problem, so that we're going to answer any query that belongs to A, we're going to answer positively because it belongs to the halting problem. And any query that turns out to belong to capital B will be answered negatively because the purpose is for B to be disjoint to the halting problem. And I'll explain how we maintain these two sets in a minute now. So here's the simulation. We simulate the program P on input X for J steps, and J is going to grow in stages. And whenever the program P makes a query to the halting Oracle H, our new simulation must not make access to the halting Oracle. Instead, it checks whether the given query belongs to A, so the argument to the function belongs to capital A. If so, it answers positively and lets the program continue with a positive answer. And those that belong to B, that should be a B, are answered negatively, and then the program continues. And since we have this condition that A is a subset of H, all queries in this way are indeed answered correctly positively. And since B is disjoint to the halting problem, all queries that belong to B are indeed justly answered negatively. But what happens if there's a query which does not belong to A nor to B? Then something important but subtle happens in our simulation. We add such a query to the set B, which is supposed to be disjoint to H and therefore to consist of problems which are of instances of the halting problem which do not terminate, right? Remember, H is a set of instances which terminate, and therefore being disjoint means all instances in B do not terminate. Now, this is emphasized as tentative. Why? Because, well, how can our simulation be sure that this instances does not actually terminate? Remember, we can only be sure about instances that terminate. Once they terminate, then we know they do. But it is fundamentally impossible for an instance of the halting problem to be known when it does not terminate. That's the hard part. Okay, and the approach here is the following: to put it tentatively into the set, and then to keep verifying while our simulation continues that all the elements we've put into the set are indeed do not belong to the halting problem. And how do we do that? Well, remember that the halting problem itself is semi-decidable, so we can kind of simulate the instance to check whether it belongs to the halting problem. Only one way, right? Whether it belongs to the halting problem can eventually be found out by simulating it. That's our interpreter approach. And if it eventually terminates, right, then we're going to move it from the set B to the set A. Remember, the set A, it will maintain it in such a way that it consists only of instances, of positive instances to the halting problem. So baseline is our new simulation without access to the halting problem. In this way, replaces all queries to the querying the internal and finite set A and B. And if this simulation terminates, then we try again with the next stage, because we cannot be sure yet whether the answer given by our simulation is correct. There could be some negative instances of the halting problem that we have tentatively but wrongly put into here. So while proceeding with this simulating the algorithm with Oracle access to the halting problem, we simultaneously keep kind of verifying, semi-deciding all the queries that we have answered positively because we have put them into the set B. And if any of them eventually turns out to terminate, then that means we have wrongly put them into B, because as you remember here, B should be disjoint from the halting problem. No element of B should ever terminate. But if our simulation, parallel to our simulation, remember we alternate execution. If our simulation ever turns out, reveals that this does terminate, then we quickly move it from the wrong set B to the right set A. Okay, that's the idea. When the query turns out to be an instance, a positive instance of the halting problem, then we have made a mistake. We had put it into the set B of negative instances to the halting problem. We may have answered queries negatively to the set, but that may have been a mistake, because eventually we realize that the instances does belong to H. In this case, we move it from B to the set A, which is supposed to be a subset of the halting problem. We remove it from B, which is now again purportedly disjoint to the halting problem, and we try again with a different value of J, with an increased value of J, because we can try again infinitely many times. We only need to compute the actual value in the limit eventually, and we don't need to worry about when that eventually happens. So this is kind of concludes the proof sketch of the Schoenfeld limit lemma, which says that given Oracle access to the halting problem is equivalent to being able to compute something eventually only in the limit computability. That's also something that people in artificial intelligence considered, like for instance Frank Stefan in Singapore. Okay, anyway, final slide of the recap on computability theory. Namely, a hierarchy, reiterating this. So I pointed out and introduced the oracle version of the halting problem in the question whether a given while program with oracle access terminates or not. And when this oracle is the halting oracle, then this cannot be replaced by anything decidable. But this halting oracle is strictly harder. Maybe one can prove that it is actually equivalent to the totality problem. And we can iterate that and consider H prime as oracle. Right here, H is the oracle. We can consider H prime as oracle, and this turns out to be even more powerful than just H as oracle, and so on. An entire hierarchy, and this is the famous arithmetic hierarchy. So the lowest level of that hierarchy is comprised of the decidable sets. So these Greek letters with indices denote subsets of natural numbers, namely decidable ones, all the three the same. And this looks like this. On the bottom, that's the class of decidable sets. Next step up is the class of semi-decidable sets. That is the class of sets that are decidable when given oracle access to the halting problem, or more generally and iteratively, the K plus first level consists of all those problems that are decidable when given oracle access to the kth, namely one level lower of the arithmetic hierarchy, or equivalently pi k, which I'll introduce on the next two lines. So if we have this hierarchy, and this hierarchy can be shown to be actually strict. So unlike in P versus NP, where we have a similar hierarchy, but we cannot prove that this hierarchy is strict, here the hierarchy is provably strict. Namely, that's basically shown by readapting, by recalling our proof that the halting problem is undecidable. The same works for problems to be undecidable given access to any fixed oracle. And this class of problems that are decidable when given access to some undecidable problem, this is easily seen to be closed under composition, which is expressed here. And the hierarchy climbs up or proceeds by considering problems that are semi-decidable when given oracle access to some undecidable problem, sigma k. And similarly, co-semi-decidable, these are the complements. And so let me sketch the hierarchy. These are kind of like the computable counterparts to NP. One can guess and verify, and co-NP, that's the complements of NP. But unlike in complexity theory, which we'll return to later in this course, these are strict supersets, both, as can actually be proven, and they are actually different. So generally, in this way, one obtains a proper infinite hierarchy, which is called the arithmetic hierarchy. Okay, so this concludes our discussion of classical, that is discrete, computability theory. So we've talked about uncomputability of the halting problem. We've discussed semi-decidability, the notion, and its property, justified the notion. We've talked about reduction as a means to compare discrete decision problems. We've formalized our model of computation as a while program instead of the Turing machine. We discussed the SMN property, which is basically means type conversion or currying. And we've discussed the universal Turing machine UTM property. We then talked about oracle computation, which is here amounts to while programs given access to some external function, computable or not, and we've investigated the computational power added to a while program when it is given oracle access to such an uncomputable external function. And we've demonstrated the Schoenfield's limit lemma, which basically says eventual convergence without rate of convergence is as powerful as given Oracle access to the holding problem, and we'll see that in the real setting of numerics, this is also true, namely when approximating a continuous problem without error bounds, that's as weak as saying that something is computable if we are given access to the holding problem, which of course in practice we are not, so it's very weak. And finally, we've iterated that and thus arrived at the arithmetic hierarchy. So that's kind of ends and wraps up the first recap part of namely the computability theoretical recap part of this lecture.